All right, I'm going to run through all this stuff for this test as fast as possible. I'm going to start with this as well. Josh's slides are extremely comprehensive. I would highly recommend going through his slides, working through those. It will help you a lot on the test, I believe. This is also a good supplemental thing to listen to. But if you did go to Josh's review, I'm guessing a lot of this covers for the most part, we'll be covering the same stuff. But if you didn't go to Josh's reviews, please look at his slides, go through his practice problems. That'll probably be one of the best ways to study. He put a lot of time into those, so they'll do you some good. All right, to start off, talking about radicals, we're going to start with the second point, be able to identify radical initiation and conditions, propagation and termination events in a mechanism. All right, so the initiation of a radical reaction, it's too small. So the initiation of a radical reaction is how the radicals are created, as you can see right here, from a molecule that originally has no radicals, such as Br2, the HBr, or the NBS. Typically you use light, as in all of these. I believe with the peroxide you can use light or heat. I think most commonly you see heat. So I'd say stick to heat if you have to choose. So the initiation step, the way I like to remember it, you start with no radical, you finish with radicals. Propagation, you start with radicals. You start with these right here, and then you're going to end with more radicals. When you're doing these, when you're drawing out the mechanism, I'm guessing there will be a radical question on the test for mechanism-wise. Make sure that you have at least 2 propagation steps. I'm sure she'll include that on there. So a propagation step could be just like this, where the Br comes in and forms the HBr off of this. And then forms that radical right here as well. And then, because this one is allelic, you can have that kind of come in and do that resonance structure, form that other radical right here, form another radical right here. So these are all propagation steps where you start with a radical, as in like right here, you have this radical right here, and in the end you have another radical. Something really important with this is the notation. A lot of you guys on the recitation sheet got this wrong. You have to have this fishhook type arrow. If you have a double arrow like that is wrong. That signifies the transfer of 2 electrons. Radicals, we're talking about 1 electron. So for this specific case, a lot of the times you can use this Br2 to start the radical reaction, or Cl2. But if you're using an allelic molecule, such as this, it's got this in the resonance right there, double bond right here, right there. For allelic bromination, you have to use NBS. NBS kind of allows for like a steady release of bromine radical. It provides a steady concentration of this, while if you use this, it's kind of like not very steady concentration. And also, as you guys have learned in the past, if you put Br2 with this, you're going to end up with dibromide, where there's Br right here and Br right there. So if you have an allelic bromination and you want the bromine to end up on this carbon right here, then you have to use NBS, which provides a steady concentration of Br2. All right, so then some more halogenation. If you're doing chlorination, all products are formed. So you have Cl2, HV, all products are formed because chlorine is a more reactive radical than bromine is, I believe. Kind of just goes all over. I don't know exactly the reason. Just remember chlorination, all the possible products. So like, if you look at this molecule, we can have radical right here, radical right here, radical right here, radical right here. This and this are the same, so it's only one of these. With bromination, you're going to form the most substituted radical, where you're going to end up with this radical, which then is going to form that. And this is the tertiary. If the most substituted was like this, a secondary, the radical would form right here. With chlorine, there is going to be a major product, and it will be the most substituted. This would be probably the second most concentrated, and these two would probably be about the same. All right, so anti-Markovnikov with alkenes, bromination. With this, you want to use HBr and peroxided heat. And in the presence of the peroxides, the HBr adds to an alkene in the anti-Markovnikov fashion, where Br is going to go on the less substituted carbon, on this one right here, of the alkene. And this is because the bromine radical adds to the alkene first to generate the more stable carbon radical. So as you can see right here, the bromine is going to add to that radical before, like as soon as possible, first things first, rather than the hydrogen. And then it's going to form the more stable radical, which will be on the more substituted side. And then that is going to be terminated like that. Actually, that's a propagation step, I suppose, because you're going to end with another bromine radical right here. And then this is the termination step, where starting with radicals, ending with no radicals. Cool. Now we're going to talk a little about polymers. The study guide says identify monomers used for different types of polymers. Identify what monomer a polymer is made from. This is pretty tough, but once you get it, it kind of becomes pretty simple. So a monomer right here is a single subunit in a polymer. I think that the easiest way to find what the monomer is, with the polymer, you're typically going to have this zigzag backbone like this. So what I would do if I were you guys, I would label them A, B, A, B, A, B. And then I'd come over here and then draw that double bond. Label your first one A, your second one B. And then you know on B, or on A, you have this whole shebangle thing. You can just draw, from there you can go Cl. And then you can see that you got that. And then there you go. That's the monomer for this. By labeling it AB, it becomes a lot easier. You can do it in reverse as well, where you start with the monomer and go A, B. Oh, that's backwards. Just make sure it's consistent. Color those. Hopefully that makes sense. And as you can see, this molecule is the same as that molecule, just kind of flipped. Yeah, it's the same. Cool. So yeah, label them AB, AB, AB. You can do the same thing for all of these. I'll go BA. Then as you can see over here, you got A, B, B. Makes it really easy. Cool. So chain growth polymer, or polymerization, is through the radicals. You start with the peroxide and heat to start it, and then the peroxide reacts with that double bond forms the radical onto the more substituted carbon, which is going to do that same thing with another of the same molecule. And it's just going to keep going like that over and over again into infinity. The cationic, I don't remember this one very well, but this is exactly what she had written. So I trust that it's correct. But the OH2 is going to react with this bromine molecule, or not bromine, boron molecule, and form this positively charged OH2 group. Then the double bond is going to come and pick up one of these H's. You notice that this is not a fishhook. This is both the electrons, which will form a carbon cation right there, and that H is going to be on this side right here. And then with that carbon cation, or carbocation, you're going to get the same thing happening over and over again, repeating. And I would say do the AB thing again every single time. The anionic is essentially the opposite of this. The radical reaction starts by nucleophilic attack, where Grignard reagent or something like that, super strong nucleophile, comes in and attacks the the electrophilic double bond. So just something to state is the double bond right there can act as an electrophile or a nucleophile, but it's dependent on what we have in solution. So then you're going to form this anion right here on, once again, the more substituted carbon. And then that anion is going to come and attack an equivalent of that, and it's going to keep happening into infinity until it is terminated with a workup step. There we go. Yeah, so it's terminated by a workup step right here with the water, which will form something like that. A lot more of these, though. At epoxide, polymerization starts with an epoxide and a strong base, where the strong base is going to open it up, as you guys know, from the less substituted side. And then it's going to form this negatively charged oxygen, which is still basic, nucleophilic. It's going to attack the less substituted side again, over and over again. This one's a little bit different from the AB. I would say this one, the way to go is A, B, and then you can just say O. It's going to be confusing. O. So then the final product will be ABO, rather than AB. And that's because the backbone is going to be 3, which is this right here. Or actually, it's going to be this. My bad. AB, A. All right, then copolymers. Copolymers happen when there's two different alkenes that polymerize together. Ideally, it goes back and forth like this, I guess, and like that's what researchers and those synthetic chemists want to do. But in reality, this is what happens. This is like the cartoon animation thing, where you got like 2 of this one and then 1 of that one, and it's kind of randomized. She might ask a question about that, about copolymers. I know it was on the recitation sheet, so if that's confusing, go back and look at that recitation sheet. Look at the key. Condensation polymers are using a, what is it called? It's called carbonyl substitution. That's what it is. That's wrong, isn't it? Nucleophilic substitution is kind of the same. Where this will come in and attack that. And then that will pop back up and then pop back down. and now break off as a leaving group. And then it's going to do that on both sides. And eventually you're going to form something like this. Where it just keeps going, as always, into infinity. Not really into infinity. There are limits to polymerization, but very large molecules. Cool. So I think that's everything with polymerization. I think that's all for chapter 31 or 13 and 31. Let me read through these real quick. No mechanisms, including radical polymerization. So you want to know the mechanisms for cationic, anionic, just regular radical polymerization. I don't think you need to know the mechanism for copolymers. But I think, that's the same. I don't think you need to know the mechanism for condensation polymers, but you should know. Actually, it does say including the mechanism. So yeah, this is the mechanism. It's just the same as the carbonyl substitution. All right, chapter 14. Conjugation, resonance, all that type of stuff. So we're going to have to rewrite the stability rules a little bit that you guys learned about for carbocations, because we're going to include an alkene in there now. So to start, I'll just start, I'm going to go back. So chapter 14, I'm going to read off the concepts. Recognize patterns of resonance and be able to draw correct resonance structures with correct arrow pushing and identify the major and minor structures. This was already talked about in the past on the first test. Don't break sigma bonds, follow the octet rule. Major contributors are full octets on all atoms. You're minimizing the formal charge. And the negative charge on electronegative atoms and positive charge on electropositive atoms are going to be the major contributors. So if you don't remember that, go back and study from the first test. Number 2 is discuss and identify increased stabilization of allyl carbocations or carbanions. Understand the concept of conjugation. P orbital conjugation leads to electron delocalization. All right, so now we're back to the stability. As you know, primary carbocation is the least stable. And then the allylic carbocation is actually going to be, this is still a primary carbocation, but it's going to be about equal to a secondary carbocation stability, and that's because there is this resonance right here. You could have that plus right there and the double bond right there. Cool. And then that is still less stable than a tertiary carbocation. And then a quick thing with stereochemistry. Kind of the same as you learned in the past, except for now we have S-trans and S-cis. And the S is talking about the sigma bonds, specifically how the double bonds are oriented around the sigma bond. So this is S-trans because these are trans to each other. This one is S-cis because these are cis to each other. And you can change the sigma bond orientation as much as you want because you can freely rotate around this. You cannot change this orientation. So if you change the orientation of the S-trans, S-cis, rotating around the sigma bond, they're going to be conformers, provided that these all stay the same. If these change, then you're either going to have an enantiomer or diastereomer, depending on how many are changed. So remember that. If it's only changing this conformation of the sigma bonds, conformers. All right, recognize the unique 1,4 electrophilic addition of the 1,3 dienes and be able to explain it by drawing the intermediate resonance structures. Identify the kinetic and thermodynamic products. So 1,4 versus 1,2 addition with 1,3 dienes. What is a 1,3 diene? There's 1, 2, 3, 4, so it's 1, 3. Because there's 2 double bonds, 1,3 diene. Now I'm gonna change that real quick. This should be HBr. So when we're talking about 1,4 versus 1,2 addition, we're talking about whether the H and the Br will add to the 1, 2 or the 1, 4. And we'll talk about that more in depth. So to start off, because this is acidic, this will act as a nucleophile. This will be the electrophile, and this will come in and attack the H, which will break that bond onto the Br and form this carbocation right here. And that's a pretty stable carbocation right there. So going this way, nothing changes. I just redrew the molecule right here. Then the bromine is going to come in and do that. And you're going to form this product that is called the kinetic product. And why is it the kinetic product? It's because this carbocation is pretty stable. This is a stable carbocation, which means that the activation energy to get to this carbocation will be lower. The rate determining step is going to be this, and is going to be determined by the stability of that carbocation. Now let's just say we do a resonance structure where we move that double bond over, change the position of our carbocation. This will be a less stable carbocation. It will still happen. That doesn't look like a very good arrow. It'll still happen. Bromine will come in, do that nucleophilic attack on that carbocation, and form this product. Now, if we compare this product and this product, the stability and the energy level, you look at this double bond, this is tri-substituted, which means it's a pretty stable molecule, while this one is only di-substituted. So this will be a less stable molecule than this one because this double bond is more substituted. While this molecule will react faster because the activation energy is lower because it has a more stable carbocation. As you can see, this added a hydrogen right there. And then the bromine is right here. So this is 1, 2 addition. The 1, 2 addition will most likely be the kinetic product. And then this one, you can see hydrogen still added right there. And it's going to be the 1, 2, 3, 4 product, which is the thermodynamic product because this is more stable, more energetically favorable. I'm going to try to be consistent real quick. Avoid confusion. One, 2, 3. Cool. Now let's talk about Diels-Alder. This was a while ago, so a lot of you probably have forgotten about this. Oh shoot, I forgot a lot. Okay, that's better. So Diels-Alder, you're going to have two molecules, one diene and then one alkene. So the diene is going to act as the nucleophile, and then the dienophile is going to act as the electrophile. Electron poor, electron rich. So the mechanism is basically this is going to fall back into there. This one is going to come in and bind with that carbon, and then this double bond is going to come and bond with that carbon, which is going to form a funky looking thing like this. A lot of you guys got this wrong because it's really hard to draw these without practice. I would recommend that you number all of your carbons to make sure you don't lose your carbons on this one especially. So 1, 2, 3, 4, 5, 6, and then 1, 2. So you know 1 binds with 2, and 2, you're going to know 1, or I want to do different numbers. Seven, 8. So you know that seven is going to form a bond with 2, 5 is going to form a bond with 8. So then you can come over here and see that this is 8. Oh. This is 7. This is 2, 3, 4, 5. And you can see that you have 1 and 6 left. Because 7 binds with 2, 8 binds with 5. The 1 and 6 kind of just pop up. And kind of look, and it will look like that. And since this you can flip this over, it can form both of these products. One thing that's easy to remember, if the diene is a ring, you're always going to have a funky looking thing up here. If it's just like this, it's not going to look all weird. So I drew another example. This is a really common diene, pentadiene. I'm going to number all the carbons again. And then those will bond. So it'll look something like that. All right, and now how can you know if a molecule will act as a diene in a Diels-Alder reaction, or it's just a regular diene that won't work? So this is a diene, it has 2 double bonds. And first thing you know, they have to be conjugated. It has to be a 1,3 diene. Second thing, it has to be cis. So these are cis to each other. This one is S trans. So because of that, that will not work. This one is also S trans. So that also won't work. But if you notice this one, if you look at this one, you can see that this can freely rotate around that sigma bond and form this, which will be S cis, which will be great. This one, on the other hand, it's stuck in a ring. You can't rotate around this, so this just won't work. All right, now looking at the dienophiles, how reactive the dienophiles are and how quickly they'll react with a diene. This is a little bit counterintuitive because typically you'd think like, oh, the most substituted is the least reactive and the least substituted is the most reactive. But that's not necessarily how it works. It's more about the electron withdrawing and donating groups. As you see, this has 4 carbon groups. These are 4 electron donating groups, meaning that it kind of pushes electrons towards the middle. You want this double bond to act as an electrophile, so that makes it really slow, terrible reacting, probably won't actually react at all. So that's the slowest. Then this one is less substituted, less electron donating groups, so it reacts faster. This one has nothing, so kind of intermediate. Now this one has an electron withdrawing group, meaning that it will react faster than this one, and this one. And then finally this one is completely covered in electron withdrawing groups. So that double bond right here is super electron poor. This is a great dienophile. That's basically everything with the Diels-Alder. All right, moving on to chapter 15. Aromaticity. So to start, it talks about, it says, know the rules for what makes a compound aromatic and be able to identify where a molecule is aromatic, anti-aromatic, or non-aromatic. I think she said you guys don't really need to know anti-aromatic. I think I'll just talk about it a little bit because it will be on the final. I don't think it's going to be on this test. So we're going to use it based on Huckel's rule and then this other rule. I don't know what it's called. It's just the other rule. So we have this little formula where 4n plus 2 equals the number of pi electrons. That's what Huckel's rule is. So if n equals 0, 1, 2, 3, into infinity, the molecule, maybe not into an infinity, I don't know about that. You guys get the point. Just integers, then aromatic. While if n, you can know it's anti-aromatic if n is an integer following this formula, perfect. So let's do some examples. So we have pi electrons. These are ones that are free to be resonating. All of these ones are. So you have 1, 2, 3, 4, 5, 6. So this is 6 aromatic. Because if you do that little equation, 4n plus 2 equals 6. 4n, so n will equal 1. This one, there's also 1, 2, 3, 4, 5, 6. Same number, so it's aromatic. This one is 1, 2, 3, 4. 4n plus 2 equals number of electrons. So there's 4 right here. N would equal a half. So this is not aromatic. Let's check if it's anti-aromatic. 4n equals 4. Obviously, n will equal 1. So this is anti-aromatic. Now let's look at this one. You have to look really closely at this one. So you obviously have 1, 2, 3, 4 pi electrons. And then you know that there's, 4 extra electrons on this oxygen. How do you know if they're pi electrons? Can they resonate? So if they're resonating like this, that means that this has to be sp2 hybridized. So then that extra pair of electrons will be in a p orbital, or they'll be in a pi orbital. Yeah, I think that's right. So then you can count 2 of these, 1, 2, 3, 4, 5, 6. So this is 6. And then look at this one. So you have 1, 2, 3, 4, 5, 6, 7, 8. No, because these ones can't resonate because there'd be too many bonds. So this is just sp. Let me think. That's sp2 hybridized, but these are in a p orbital and not in a pi orbital. Yeah, so I messed up. These are in a pi orbital. These ones are in a p orbital. They're kind of stuck there. They can't resonate. Now, if you look at this one, we have those orbital, or those and those. Following that same rule, these can resonate, kind of break in. These ones cannot resonate. These are stuck in a p orbital. These are in a pi orbital, meaning that these electrons count, these ones don't, meaning there's 6. So that is also aromatic. So all of them are aromatic except for that one. Kind of a lame little practice. All right, now and then non-aromatic. You know it's non-aromatic if it doesn't have, or if it has like an sp3 hybridized carbon in the ring. So if it looks like this, sp3, non-aromatic. All right, electrophilic aromatic substitution. So the general mechanism, you've got to know this general mechanism. The aromatic ring acts as a nucleophile attacks an electrophile, leading to a positive carbocation right here. And then an elimination reaction restores that double bond, resulting in the substitution of an electron, or substitution of a hydrogen with an electrophile. Number 4 of that chapter is influence of substituents on a benzene ring for electrophilic aromatic substitution. Which substituents are OP activators, OP deactivators, or M deactivators? How does resonance and induction predict if a group is an activator or deactivator? All right, so all of the activators, something I found is that all of the activators, except for this one, they have a lone pair right next to, on the carbon that's alpha to the benzene ring. So for instance, I'll draw this out. You're going to have this one. Sorry for the terrible quality of this picture. It's from my notes in OChem, which I just took pictures of stuff that's going on. So you have this, and this has a pair of electrons right here. So this can collapse in, which can allow it to kind of form that, which will look like this. And this is in the ortho position, as you can see right here. So the negatively charged, this is the nucleophile, so that negatively charged ortho position makes it, what directs it right here. Obviously, oxygen will also have an inductive effect, but the fact that it can resonate like this is more powerful than that inductive effect. So it will be an ortho para director. Para because you can keep resonating, go farther, and end up with that negative charge right here. So all of these, except for the carbon, they all have a lone pair right next to it. And that makes it really easy to tell without having to memorize everything. These, the carbon, like the R group, they're weak activators, more due to like inductive effect. And then all M directors, so something that you guys don't really need to know is this. All meta-directors will shut down the Friedel-Crafts alkylation or acylation. You don't really need to know that because she never really talked about it. But this will be important to know probably for the final. Like not super crucial, but just understand, just remember that if it's a withdrawing group, the alkylation and acylation won't happen. And we'll get to what those are in just a second. But the deactivating groups are all groups where, I'll just do the first one. Where there's an inductive effect, first off, that pulls the electron density away from the ring. And when you do the resonance structure, you're going to have something that looks like this. There's a positive charge on a nucleophile, which is really bad. So it's going to force the reaction away from this position, and basically, due to it not working right here, it has to happen here. That being said, because that is how it directs meta, the reaction will also happen slower, because overall it is pulling electrons away from the ring. So meta directors, the deactivating substituents, will result in slower electrophilic aromatic substitution than the electron donating or the activating groups will. Yeah, so just practice these. I don't know if it's super important that you know the exact order of all of these, but I would kind of like, I don't know, just think about it, write it down a few times. Try to remember the general order, the general gist of that. You can even think of ways to come up with that logically. So now here are all the electrophilic aromatic substitution reactions. So with this, I think her notes are great. I'd just say go look at her guided notes or go look at Josh's practice slides with this. And you'll get a good grasp of everything you're supposed to know for this just by looking at her notes. This is just kind of like the summary of it all. The 5 different reactions. I think it's good to know the mechanisms for these 4. I highlighted those 4, but I don't think you need to know the mechanism for that. And kind of connecting these 2 ideas, if there is an activating ortho paradirector, then if it's already on here, so let's just say there's an activator like O. We'll do that one again. This X, like that's not there, will only add to that or to that. So that's kind of the application. You're not going to get a meta product if there's an activator on the ring. But yeah, I just say go look at her guided notes for that. Because 17 and 22 are beast. All right, to start, know the reducing agents for carbonyls, lithium aluminum hydride and sodium borehydride, and know how they react. Know how to synthesize carbonyl compounds from primary and secondary alcohols, ozonolysis of alkenes and alkynes, and hydration of alkynes. All right, reduction. You guys already know most of this, so I'm not going to go into great detail with this. I attached this little chart that I had made when I took OChem 2, just to kind of remember. Basically, NaBH4, sodium borohydride, will reduce aldehydes and ketones. It won't do much else. So it doesn't really touch the esters, the acids. Lithium aluminum hydride is really strong. It reduces aldehydes, ketones, esters, carboxylic acids, and it does all of that for the most part, all the way to alcohols. Like with an amide, you're going to have this right here. And basically it's going to end up with that. It just fully removes that CO. So that's something, just keep in mind that lithium aluminum hydride is really strong. It'll probably reduce basically everything. Sodium borohydride is weak. It won't reduce much. Remember the mechanism for that. I think you guys already had learned that as well, where this basically donates an H-. Same with that. Yeah, so she attached those new mechanisms. If you want to be really confident about that, go look at the slides, go look at Josh's slides, and go look at her notes on that. It's pretty comprehensive. Once again, oxidation, PCC, you already learned all of that. It stops at an aldehyde from a primary alcohol. And then the KMNO4 oxidizes all the way to carboxylic acids from the primary alcohol. And then the secondary alcohols, they both do the same. Ozonolysis cleaves the alkenes and the alkynes. Alkyne hydration, you guys already learned that as well, with an acid or with the BH3 and peroxide. So with all that, go look at her notes, go study your past notes. You learned most of this already. So sorry I'm not going into detail. There's just a lot of other stuff to get through. It's more important, or not more important, just more, I don't know, less talked about. You guys haven't learned it as much. All right, unrecognized reagents for the formation of organometallics, the Grignard, organolithium, and organocuprate. Understand how they react as nucleophiles with carbonyl compounds. All right, so organolithium is right here. Is just taking, what is that called? I don't know, alkane with the halogen, and converting it to this really strong negatively charged. So let's have this. So this really strong negatively charged alkane, yeah, probably alkane. Really strongly negatively charged alkane that will act as a nucleophile. And this is kind of how you make it to equivalence of lithium, because the other lithium will balance that bromine, the negative charge. I don't think you need to know the mechanism for that. Just kind of like know this. The Grignard reagent is doing the exact same thing, just makes that really negatively charged R group, and that magnesium is a 2+. So it will be balancing the bromine and the R, so you only need one equivalent of that. And then organolithium and Grignard reagents. Oh yeah, well, this is the organocuprate. Where you're going to take two organolithiums, two equivalents of that, react it with a copper bromide, copper halogen, and you're going to form an organocuprate, as seen right here. Yeah. So I guess just kind of know that. I don't really think there's any good way to talk about that other than just kind of memorize it. And then this is how they react. They basically react as super strong nucleophiles, and they will participate in most of the reactions you've learned, just acting as that strong nucleophile. So this will come in and as the strong nucleophile into this electrophilic carbon and bump those electrons up, form this intermediate, and then that will collapse back down, break that Cl. That is carbonyl substitution, which we'll talk about more in depth later. All right, nucleophilic addition. Understand the acidic and basic addition mechanism for the nucleophilic addition to aldehydes and ketones, be able to draw the mechanism. So one thing that I think almost is always true, you have a carbonyl in an acidic environment. What's going to happen first? The O will be protonated by the acid. So the nucleophile, this O will come in and attack this. That will almost always happen and almost always be the first thing that happens. That's just good to know. And also, one good thing to know, you're in an acidic environment. What does that mean? You're going to have a lot of plus charges, a lot of protons. Maybe not free protons, but they'll be attached to water. That being said, you don't want there to be a negative charged intermediate. That just won't work out because you have positively charged solution everywhere else. So you want to avoid that. That's one of the reasons this is the first thing that happens. So that happens, then you're going to have this positively charged group right here, the OH2 positive, and then this is going to come in, act as your nucleophile, and then knock these electrons up. And as you can see, there's no negative charge because it is already protonated before. And then you're going to have this, which is positively charged, and then there's just going to be deprotonation by more water, form that. In the basic environment, it's the opposite. I should organize this. I'll try to organize this before I send it to you guys a little bit more. But the basic environment is the opposite. You've got a lot of negative charges. So negative charges are fine. And because of that, first thing that happens, negatively charged OH comes in, attacks that. and knocks those electrons up. And then that negatively charged oxygen will be protonated by water because OH minus is always in the presence of water. Then it will form this, the diol. And then here are some other reactions. I don't remember talking about these a lot, but they're in the bottom of her guided notes, so I assume she did. Because I also am not paying attention 100% of the time. Sometimes I'm grading tests and stuff or grading recitation sheets during class. So this one, you have a cyanide, sodium cyanide, and that will come in, act as a nucleophile, and do a substitution, knock that chlorine off, and just form that. And then this one, you're going to use an organolithium or a Grignard reagent. This is a Grignard reagent, and that's going to act as the nucleophile, which will attack a carbon dioxide, the CO2, and is going to form this right here, which will then need a workup step to form a carboxylic acid. And then we have this one where you have that cyanide. I actually use this. This is a continuation. So you have that cyanide right here, and then you have the LAH, which you know is going to be reducing everything. So it's going to reduce this double or triple bond into a single bond and add hydrogens basically everywhere because that's what reducing does. And this is the mechanism for that. I don't think you'll need to know that really well, but I kept it there just because a lot of the times it's easier to remember something if you know the mechanism. All right, let me find where we were. Understand and predict the products for reactions of carboxylic acids and derivatives for nucleophilic substitution reactions. All right, yes, nucleophilic substitution reactions. This is the general reaction mechanism. So this will come in and attack, the nucleophile will come in and attack the electrophilic point, the electrophilic carbon, because of that dipole. And then this double bond, these electrons will break up first and form this intermediate. This is a tetrahedral intermediate. This is sterically hindered. You kind of want to get rid of that steric hindrance. And because of that, this negative charge on the oxygen is going to come back down and form. Once again, you got this tertiary looking thing and knock that leaving group off. You might wonder, why doesn't this just come in and immediately knock the leaving group off? If you remember HOMO-LUMO, this is a lower energy LUMO. So this will break first. It will break before this breaks. And that's why this happens before this breaks off. So that's a generalized mechanism. Understand and predict the reactivity trends of carboxylic acids and derivatives. Know the order of increasing reactivity from acid chlorides to aldehydes and ketones to esters and amides, and understand what makes one more reactive than the other. So I kind of have this right here. This is the order of reactivity of all of the things you will need to know. This was also from my notes from when I took OChem 2. This is the lowest energy molecule. And I'm specifically talking about this bond right here. All of these circles, these are signifying a leaving group. So this is the lowest energy bond. What does that mean? That is the least likely bond to break. So this is the most stable of those molecules. So typically, you're going to see all reactions go downhill. All these reactions are going to be downhill. If you're going to put an acyl chloride in the presence of, for instance, an ROH, you're going to fall back down and react with this. It's going to follow the same mechanism, but you're going to go down to this, and it's going to form that product. So all of these reactions will be going downhill with two exceptions. The exceptions are first Sokal, which is going to bring this OH bond all the way to the top, which is fantastic in synthesis reactions. If you have a carboxylic acid to start and you need to form something that looks like this, you can always start with the Sockle, which will bring it all the way back up, and then you can do that downhill reaction to bring it that way. And then there's this one, and where is this? Yeah, so this allows for a carbon or an alcohol to replace this alcohol and in the end form an ester. And it does that by protonating this O to start with, which will make, wait, let me think about that. It will protonate this OH group after this ROH group attacks this, which will make this the better leaving group than this, so it can form that. I don't know if that made sense. I don't think she talked about the mechanism for that one too much, but I think that's just enough information, knowing that acid and an alcohol will allow you to go from a carboxylic acid to an ester. Uphill reaction. All right, recognize and predict reactions at the alpha carbon of carbonyls to form enolates and how the enolate acts as a nucleophile. Identify conditions for the formation of the kinetic or thermodynamic enolate. All right, carbonyl at the alpha carbon. I'm gonna highlight these. Getting a little tired. We can make it through. All right, so what is the alpha carbon? So this right here is the functional group. This is your carbonyl. So then the alpha carbon is going to be the first carbon away from your carbonyl, which will be this one and this one. So you actually have two. I'm going to highlight both of them. So what is special about the alpha carbon? This hydrogen is going to be more acidic than a regular hydrogen off of an alkane. And that's because the conjugate base will form an enolate, which is basically conjugated or a resonance stabilized structure. So this is the enolate form right here. This is the ketone form. And the ketone is actually less stable if it's negatively charged than the enolate, because you want your negative charge on the most electronegative atom. So yeah, so this hydrogen is extra acidic, which means that it can be taken off with a strong base. So NaH is a great strong base that you can use to remove that acidic hydrogen. And then you're going to form this enolate, and then that can be reactive in basically the same way a regular nucleophile is. So this will break down and attack that. You might wonder, why wouldn't this just act as the nucleophile rather than doing this whole thing? And that's because there should be a protecting group. But you guys haven't talked about that, so you just have to accept it, and that's the way it is. So yeah, this is going to come in and attack that carbon in a regular nucleophilic attack and increase the carbon chain length. Super useful. So then there's some other similar reactions. This one you don't really need to know the mechanism, just know that with the bromination, you can end up with adding a bromine to the alpha carbon. And then with this one is really interesting. It's an aldol reaction. Same thing, you're going to form the enolate right here with a strong base. And then that is going to collapse down, and this is going to attack an aldehyde, because that's the other thing you put in there. And this is the most electrophilic carbon, and it's going to end up forming this structure with, I don't remember what you call this, but I think it's like a beta hydroxy ketone, and it's just an aldol. And it's beta hydroxy because it's alpha beta. Beta carbon has the alcohol group right there. So that one's really interesting because you can also do this reaction with just excess ketone. So if you just had a bunch of this, you could do the same reaction where this would come in and attack that instead of this. That was on one of the recitations. I'm sure you guys remember it. If not, I think it'd be super useful to go back and look at that problem. And that reminds me of something, actually. And now you can take that reaction further. I don't think I talked about this. I'm going to move all this stuff down. So now you have this aldol. If you keep adding a strong base, let me go find it just to make sure I don't lead you astray. I don't know if it's in the study guide. Well, if you keep adding a base, you can actually do an elimination reaction. So we'll just say you added more base. The most acidic hydrogen will still be right here in the middle, and it's going to come in and attack that. And because the whole thing is in like a pretty basic environment, you're actually going to make this OH a leaving group, which is not typically a good leaving group, and end up with this right here, which is the condensation. That was also in the homework. So go back and look at that recitation if that was too fast. All right, now we're going to talk about the kinetic enolate formation and the thermodynamic enolate formation. So you have LDA, which is a really strong base. It looks like this. This is LDA. It's a strong base, and it's really bulky. It has two isopropyl groups off to the side. Lithium di, whatever that is, isopropyl? I don't know. But it's a strong, bulky base. And it's going to be so bulky that it doesn't want to go to the more sterically hindered center. So it's going to go to the one of these hydrogens because they're more available sterically. And this will happen pretty quickly. So you want it at like a really cold temperature to prevent this hydrogen from being removed. And then you're going to form this, which is the least substituted enolate. And this is the kinetic product because it will happen fast. The thermodynamic product will form the more stable enolate and is basically all the other bases. But it won't happen as fast. This enolate is definitely more stable than that enolate because that double bond is way more substituted. Recognize the decarboxylation of ethyl ester and the derivatives of this reaction. Oh, is this the last thing? We are almost there. So this is, what is this called? This molecule right here, malonate ester. Right here is a malonate ester. So you're gonna have a negatively charged OH come in and attack, like if it's, oh, that looks weird. I do want it just to be H minus, not OH. So you have the H minus come in and attack this hydrogen. So what is interesting about this hydrogen? This is actually going to be even more acidic than a regular alpha carbonyl hydrogen because there are two places that this conjugate base can resonate. So this, as a conjugate base right here, can resonate up to this and also to that, which means that this hydrogen is pretty acidic. So you don't actually need quite as strong of a base, but I'd say just keep using a strong base. I don't know if the test will ask about that, but an NaH is just always great. I think. I hope so. Yeah, I think that should be fine. So what's interesting about this? You know, I'm going to take that back. One of the things she put in her notes. Sorry. I don't know if this NaH can be used, but she had this base, which is a strong base, but it's not as strong. But it actually matches this, and I think that's important, to have it match that side group. I don't remember exactly why, but I think there's some side reactions if it doesn't. Yeah, so have it match that. And then it's going to pull that hydrogen off, and once again form this enolate type structure right here. And then you have this right here added in second, and this is going to act as the nucleophile and do a substitution reaction and form this. And then you're going to do a hydrolysis type reaction where you're going to replace all of these ether groups with alcohols. She didn't write down the mechanism for that. I don't believe you need to know it. But I'm sure you guys could figure it out with your current knowledge. Understanding the fact, going back to this, understanding this and this mechanism, I'm sure you could figure out how you go from here to there. It's basically this. Oh, here we are. So you have the acid catalyzed hydrolysis, and then through heat, you're going to break off that CO2, and it's going to form this. So that one is pretty complicated, but I trust that you guys have got that. All right, so now this is one of the last things on the test, or at least that she talked about. I think she talked about it very briefly. What happens when you have an ester rather than just a regular ketone? Kind of like up there. But this one is not, I forgot what that's called, an anhydride. It's just a regular ester. So you're going to have this base come in and pull off that acidic hydrogen. Sorry, I'm slowing down. I'm getting a little tired. And form this enolate type structure. And then you see that this is an excess right here. There's excess of that. So you can then assume that, once again, this is going to act in sort of like the aldol reaction. This is going to act as the nucleophile, and this is going to act as the electrophile, the excess. And it's going to come in and attack the most electrophilic carbon. And then it's going to form this structure. And then there's, once again, this tetrahedral intermediate around this carbon, which is not as stable as this. So this is going to collapse back down. And this time, there's actually a good leaving group. So it's going to break this off, because that's a relatively good leaving group. And then it's going to form this structure. And I also forgot to draw this structure, which will probably take a water and be protonated. All right, now this is the very last thing. The alpha beta unsaturated carbonyl compound is right here. Alpha, beta, this is unsaturated. Yeah, so this is alpha to beta right here. Unsaturated carbonyl compound reacting with an enolate. This is interesting. I don't know if this was talked about in depth, but it is in there, and it will probably be on the final. So I would learn this pretty well, where this negative charge actually comes into this carbon and attacks that, and then that double bond will break down. form the double bond on this side, and this will pop back up. And then if you count the carbons, you got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You can keep track of them like that. And then you're going to have finally the workup step, and you're going to form that. All right, I think that is all. Good luck, guys. This is going to be a tough test, but every other one is also difficult. It's not going to be anything unexpected. And once again, please go back, look at Josh's slides. They'll be super helpful. Also, look at her filled-in lecture slides. Those are super helpful as well. I think most of the information that you need to know on the test is directly on those slides. Good luck. Study hard. You're going to do great.